Welcome back, everyone. Ready for another deep dive?
Always.
Today, we're going to tackle something pretty wild. Dubnium. Element 105.
Ooh, that's a good one.
Not exactly something you find just lying around, is it?
Nope, definitely not. This is a synthetic element scientists made. And the story of how they made it, well,
Sounds like there's some juicy history there.
let's just say there was a bit of drama involved. A little bit of a scientific thriller, even.
Okay, now you've got me hooked. So what are we looking at today? What's our source material for this deep dive?
We've got Dubnium's Wikipedia page, of course.
Classic.
And we've also got this really cool short article specifically about the element's history.
All right, so let's do this. Dubnium, element 105, synthesized. Where do we even begin with something like this?
Well, before we get into all the drama and intrigue, maybe we should start with the basics. How do scientists even go about making these super heavy elements that don't exist in nature?
Yeah, good point. It's not like they can just mix a few chemicals in a beaker and bam, dubnium.
Right. It's definitely not your typical chemistry experiment. It's more like, imagine trying to force two tiny, powerful magnets together.
They'd repel each other.
Exactly. And it's the same with atomic nuclei. To create dubnium, scientists had to overcome that repulsion, which is a massive challenge.
Okay, that sounds intense. How do they even do that?
Particle accelerators, these giant machines that smash lighter atoms into heavier ones at incredibly high speeds.
Whoa, like a microscopic demolition derby?
Kind of, but the stakes are way higher. And even when they do manage to fuse those nuclei, the resulting element is often incredibly unstable. It might only exist for a fraction of a second.
So it's not just about creating it, it's about detecting it before it disappears.
Exactly. It takes some seriously sensitive instruments and a whole lot of patience.
Okay, I'm starting to get a sense of just how challenging this is. But you mentioned some drama earlier, right? The discovery of dubnium.
Oh yeah, this is where the Transfermium Wars come in.
The what?
The Transfermium Wars.
Yeah.
Basically, you had two main contenders trying to synthesize dubnium.
Okay, who are we talking about?
On one side, you had the Joint Institute for Nuclear Research, or JINR, over in Dubna, Russia.
Russia, of course. And on the other side?
The Lawrence Berkeley Laboratory,
Yeah.
LBL, based in the U.S.
Ah, okay. So a bit of a Cold War science showdown.
Pretty much. And to make things even more interesting, each team was using a different method to try and synthesize dubnium.
Really? Tell me more about that.
Well, the JINR, they were bombarding americium with neon ions.
Okay, and LBL, what was their approach?
They were using californium and nitrogen ions.
Wow, two completely different approaches. So I'm guessing this is where the controversy started.
You got it. Both teams claimed to have synthesized element 105 first. The JINR reported their findings in 1968, while LBL published their results in 1970.
I can see how that would cause some tension. So who ended up getting credit?
Well, it took years of debate, with the scientific community eventually stepping in to try and mediate.
Sounds messy.
It was. They actually formed a special task force, the Transfermium Working Group, to review both teams' research and decide who actually got there first.
Wow, a scientific investigation. So what was the verdict?
In 1993, they finally announced their decision. Both teams deserved credit.
Ah, a compromise. So that settles the discovery, but what about the name? I'm guessing there were arguments about that too.
Oh, absolutely. The JINR, being located in Dubna, naturally wanted to call it Dubnium, but they actually initially suggested Niels Bohrium first, to honor Niels Bohr.
Makes sense. And LBL, I bet they had a counterproposal.
They wanted to call it Hanium.
Hanium versus Niels Bohrium. Almost sounds like a science fiction movie. So how did we end up with Dubnium?
Well, it was all part of a grand compromise to settle multiple naming disputes. In 1997, IUPAC, the International Union of Pure and Applied Chemistry, officially named element 105 Dubnium.
I see. So Dubna got its element in the end. But why all this fuss over an element we'll never actually encounter in our daily lives? What makes dubnium so special?
That's the fascinating part. Even though it's synthetic and short-lived, dubnium offers a unique window into the fundamental building blocks of matter, and its position on the periodic table, right below vanadium, niobium, and tantalum. Well, it suggests it should behave similarly, but
Oh, there's a but? Okay, I'm definitely intrigued now. What's the twist?
dubnium's massive nucleus leads to what we call relativistic effects. And those effects, well, they cause some pretty interesting deviations from what we'd expect based on its family.
Relativistic effects. Okay, now you've really got me curious. What exactly does that mean?
Think of it this way. The electrons in dubnium are moving so fast that they're practically breaking the speed limit.
Whoa, faster than a speeding electron.
Practically. And at those speeds, Einstein's theory of relativity comes into play. Those high speeds actually change the electron's behavior, which in turn affects how dubnium interacts with other elements.
So dubnium is kind of a rebel element, breaking the periodic table rules.
You could say that.
Yeah.
It certainly keeps things interesting. And that's exactly what we'll dive into next. How do these relativistic effects actually play out in dubnium's chemistry? What surprises might they hold?
All right, relativistic electrons, breaking the speed limit. I'm ready for more. But how do scientists actually study an element that exists for like a blink of an eye? It's not like they can just whip out a dubnium sample and put it under a microscope, right?
You're telling me? It's like trying to study a soap bubble before it pops. That's kind of what working with dubnium is like.
Mm-hmm.
Early on, they had to get creative. They started by looking at how easily dubnium bromide turns into a gas, its volatility.
Volatility, so like how quickly it evaporates.
Exactly. They compared it to the bromides of its neighbors on the periodic table, niobium and hafnium, to see if it acted more like a true group 5 element or went its own way.
Did it follow the family trend?
The initial results were a little fuzzy. They kind of hinted that it might be a bit of a rebel, acting more like hafnium. But those early experiments were limited by, well, the technology back then.
Yeah, I can imagine. So a bit of a blurry picture at first. What happened next? Did they eventually get a clearer view?
They did. In the 1980s, a team at LBL decided to tackle another big question. What kind of charge dubnium prefers when it forms compounds? Its oxidation state.
Oxidation state. Oh, yeah, I remember learning about those. Sort of. Refresh my memory.
Think of it as an atom's willingness to share its electrons with other atoms. Dubnium, like its buddies in group 5, was predicted to have a +5 oxidation state, meaning it likes to share 5 electrons.
Okay, so they were basically testing if dubnium was a team player, like the rest of its family.
Exactly. They designed this really clever experiment. They measured how well dubnium stuck to a glass surface compared to other elements. Kind of like, I don't know, seeing which cookie sticks to the baking sheet best.
I like that analogy. So what happened? Did dubnium pass the stickiness test?
It did. Aced it, actually. Just like a true group 5 element, it had a strong affinity for that glass surface. Confirmed that +5 oxidation state. But here's the catch. When they tried to separate dubnium from other elements using different solvents, it started acting more like niobium than tantalum.
Whoa. So it followed the family playbook in one test, but then went rogue in another. Sounds like dubnium is full of surprises.
You said it. And this points to the fact that its chemistry is being influenced by those relativistic effects we talked about earlier. Those super speedy electrons can really shake things up.
So it's not always predictable just based on its family. Did they do any more experiments to try and figure out what dubnium was up to?
Oh, definitely. Scientists don't give up easily. They brought out the big guns. Super sophisticated techniques like chromatography. Imagine separating colored dyes on filter paper, but on a much, much tinier scale.
Wow, that's incredible. So they were basically trying to break down dubnium's behavior piece by piece to really understand how it forms compounds.
Precisely. And their findings, well, let's just say dubnium kept them on their toes. Sometimes it acted like its group 5 siblings. Sometimes it completely defied expectations. In some experiments, it even showed similarities to protactinium, which is way further down the periodic table.
Really? That's wild. So even though it's in group 5, it doesn't always play by the rules. What else did those experiments reveal?
They found that dubnium's behavior could change depending on the specific conditions, like a chameleon adapting to its environment. For instance, in one experiment, dubnium really liked to form complexes with fluoride and oxygen, similar to niobium but not tantalum.
So it's picking and choosing, borrowing a little from here, a little from there.
That's one way to put it. And then, when they studied its volatility in different forms, bromides, chlorides, even oxychlorides, they uncovered even more quirks. It's like dubnium likes to keep the scientists guessing.
It's amazing how much they've learned from such tiny, short-lived samples. They must be incredibly persistent. But wait, wasn't there some exciting news recently about a longer-lived dubnium isotope?
You're right. The discovery of Dubnium-268, which has a half-life of over a day, was a huge breakthrough. It's like finally having more time to study that soap bubble before it disappears.
That must have been a game changer. Did this new isotope let them dig even deeper into dubnium's mysteries?
Absolutely. They were able to confirm that stable +5 oxidation state we talked about and explore its behavior in much more detail, like how it interacts with fluoride ions in a solution, which of course revealed even more of its unpredictable nature.
Wow, so even with a longer lifespan, dubnium is still full of surprises. Sounds like its story is far from over.
You got it. The more we learn about Dubnium, the more we realize how much more there is to discover. It just goes to show that even in the world of the periodic table, there are still uncharted territories waiting to be explored.
That's what makes science so exciting. Speaking of uncharted territory, I remember you mentioned something about the ethical considerations of creating these super heavy elements. Is there more to this story than just scientific curiosity? It really makes you think, doesn't it? Like, we can create these elements that don't even exist in nature. It's mind-blowing. But it also kind of makes you wonder, where do we draw the line?
That's a really good question. And it's one that scientists are grappling with more and more as we push further into the realm of super heavy elements. It's not just about the science anymore, it's about the bigger picture.
So what kind of questions are we talking about here?
Well, for starters, synthesizing these elements takes a lot of resources, I mean. We're talking about these incredibly sophisticated facilities, cutting-edge technology, brilliant minds, all dedicated to creating these elements that, well, they might not have any practical applications.
So it's about priorities then. Like, are we focusing on the right things? Should we be putting our resources elsewhere?
Exactly. And then there's the question of unintended consequences. When you're dealing with something that's never existed before, you can't always predict how it's going to behave.
That makes sense. I mean, even with Dubnium, we've seen how unpredictable it can be.
Right. So as we create these exotic elements, we have to be really careful. Think about the potential risks, the radioactivity, the instability, how they might interact with other elements. We're basically exploring a whole new frontier, and we have to be prepared for the unknown.
It's a bit like walking a tightrope, isn't it? Balancing the excitement of discovery with, well, a sense of responsibility.
I think that's a great way to put it. It's about asking those tough questions. What are the potential benefits? What are the risks? How do we make sure our pursuit of knowledge doesn't come at a cost to humanity or our planet?
Big questions, for sure. This deep dive has really taken us on a journey. We've gone from smashing atoms to like existential pondering about the future of science.
And that's what makes science so fascinating. It's not just about facts and figures. It's about pushing boundaries and asking those big, sometimes uncomfortable questions.
Couldn't have said it better myself. So, for you, our listener, I hope this deep dive into Dubnium has sparked your curiosity. Maybe it's made you appreciate this fleeting element that's challenging our understanding of the periodic table.
Sure.
Or maybe it's made you think about the bigger questions, the ethical considerations of creating these super heavy elements.
Because even though elements like Dubnium might seem far removed from our everyday lives, they really do offer a unique window into, well, the fundamental nature of matter, the forces that govern our universe.
And the more we understand those building blocks, the better equipped we are for the future, whatever that future may hold.
So keep asking questions, keep exploring, keep that sense of wonder alive. There's still so much out there to discover.
Until next time, happy exploring.